Hello everybody, welcome to Neural Networks and Deep Learning module. Today's learning session is on Recurrent Neural Network or RNN. Along with it, we'll also learn LSTM. We will specifically focus on the implementation of RNNs with an example using PyTorch and see the perspective of LSTM as well. For this session, our primary requirements are PyTorch, Matplotlib. We have already set up PyTorch and Matplotlib. If you do not have this installed, please recap our installation learning session first and then resume this learning session. Dataset. To download the dataset, paste this link in your browser. Copy, go to your Google Chrome. You can see dataset is getting downloaded. Show it in your folder. Extract it. In your designated folder. Then go to your data. You will find data names. All are in notepad format. So we will be building and training a character level RNN to classify words. A character level RNN reads words as a series of characters. As an output, it gives a prediction and a hidden state at each step, feeding its previous hidden state into each of the next step. We take the final prediction to be the output, that is, which class the word belongs to. Specifically, we will train on a few thousand surnames from 18 languages of origin and predict which language a name is from based on the spelling. Next, we'll show our final application, how it looks on. A surname is given as input and our RNN outputs a score regarding how certain it is. Example, our classifier says that the surname in turn is Scottish. Class score is 0.47 with more certainty than it's in English, whose class score is 1.52. Similarly, Irish score is 3.57, is even lower. The higher the score or lower the negativity it is, the better is our prediction. Now let's move to the implementation. Here we have to take the Python. So open CMD, type Jupyter Notebook. Your Jupyter Notebook opens up. Click on New, as usual Python 3. Then rename the notebook as RNN. Here we will be doing some mandatory pre-processing and sort of getting our data ready before we are good to start the next sections. So type from future import Unicode print function division. Our dataset is in Unicode literals. We will need to convert Unicode into ASCII before we start our training. From IO import open, this imports input output streams. Import globe, this imports utility to open and join our dataset. Import OS, this imports our operating system services. Def find files in bracket path, return globe path. This will return the full path of our dataset. Print find files, data name, text, close the bracket. It will print the output of our function. Next, import Unicode data, that is importing Unicode functions. Next, import string, that is it will importing our string. Then type all letters, that is string ASCII letters. Then n letters equal to len in bracket all letters. These lines will help turn our Unicode to ASCII. Don't dig too much into this code, as this is just a utility to get ready our data. Type def Unicode to ASCII. This function will finally convert our Unicode data to ASCII. Return join C for C in Unicode data, normalize NFDs, if Unicode category C, then type MN. And C in all letters. Print Unicode to ASCII as shown. Now we will build the category line dictionary, that is a list of names per language. Category lines, then all categories. This will read a file and split it into 2 lines. Type def read lines in bracket file name colon For file name, in find files, data names, text, category equal to OS path, split text, so return to Unicode to ASCII line in lines before going into category lines. Next, for file name, in find files, in bracket, data names, text, then category, equal to OS path, split text, OS path base name, in bracket file name, all categories, append, in bracket category, next lines equal to read lines, in bracket file name, category lines, in bracket category, equal to lines, then in categories, equal to len all categories. Next, click run. In case you find error, you can go to that particular line and correct it. Then again run. You can check particular syntax. Now error has been corrected, and we will build the category lines dictionary, that is a list of names per language. Now we have category lines, a dictionary mapping each category language to a list of lines in bracket names. We also kept track of all categories, just a list of languages, and n categories for later reference. Let's test whether we have everything set correctly. Print category lines in bracket Italian. As you can see, we got this output, which means everything is set up correctly. Congratulations. Now that we have all the names organized, we need to turn them into tensors to make use any of them. To represent a single letter, we use a one-hot vector of size 1 multiplied by n letters. A one-hot vector is filled with zeros except for one at index of the current letter. Example, B equal to within 0, 1, 0, 0, 0. To make a word, we join a bunch of those into a 2D matrix, line length multiplied by 1 into number n letters. That extra one dimension is because PyTorch assumes everything in batches, and we are just using a batch size of 1 here. Type import torch, find letter index from all letters. For example, A, def letter to index letter, return all letters, find letter. Now just for demonstration, we'll turn a letter into a 1 cross n letter tensors. Def letter to tensor letter, tensor equal to torch zeros 1 n letters, tensor 0 let next letter to index, type letter equal to 1. Next, return tensor. This will return the tensor. Now we'll turn a line into a line length cross 1 cross n letters, or an array into one hot letter vectors. Def line to tensor, line tensor equal to torch zeros len line 1 n letters, next for li letter in enumerate in bracket line type tensor li0 letter to index letter equal to 1, return tensor, print letter to tensor in bracket j will convert a single letter into a tensor. Then print line to tensor in bracket, type Jones, then size. This will convert the whole line into a tensor and print its size. Next, click run. You can check where from the error has originated. Then you can see and correct, and now it is giving the result. Next, let's move into creating the network. Before AutoGrad, that is automatic computation of gradient for back propagation, creating a recurrent neural network in Torch involved cloning the parameters of a layer over several time steps. The layers held hidden state and gradient, which are now entirely handled by the graph itself. This means you can implement a RNN in a very pure way as regular feed-forward layers. This RNN module is just two linear layers which operate on an input and hidden state with a log softmax layer after the output. Now that we have explained this architecture, let's move on to Python to implement this architecture. Import torch nn as nn, class rnn, nn module. This constructor will save the state of model of our object. Def init self input size, hidden size, output size. Super RNN self init then self hidden size e equal to hidden size. Self I to h n linear input size plus hidden size, then type hidden size. Type self I2O equal to nn linear input size, hidden size, output size, self next type self softmax equal to nn log softmax in bracket dimension equal to 1. We have implemented the architecture defined in the diagram. Let's define forward and backward pass of our network. Def forward self input hidden combined equal to torch cat input hidden 1 hidden equal to self I to h combined output equal to self I to O combined then output equal to self softmax output return output hidden def init hidden self then return torch zeros 1 self hidden size n hidden equal to 128 RNN equal to type RNN n letters n hidden n categories. Next run. Everything is written correctly. Now to run a step of this network, we need to pass an input, in our case the tensor for the current letter, and a previous hidden state which we initialize as zeros at first. We'll get back the output, the probability of each language, and a next hidden state which we keep for the next step. Input equal to letter to tensor, hidden equal to torch zeros, 1 n hidden output next hidden equal to RNN input hidden. Next run. For the sake of efficiency, we don't want to be creating a new tensor for every step, so we will use line to tensor instead of letter to tensor and use slices. This could be further optimized by pre-computing batches of tensors. Input equal to line to tensor. Albert hidden equal to torch zeros. 1n hidden. Output next hidden equal to RNN input 0 hidden print output. Then click run. You can see that the output is a within 1 cross n categories tensor, where every item is the likelihood of that category. Higher is more likely. Higher the value, more it will be likely. Next, let's come to the training. Before going into training, we should make a few helper function. First is to interpret the output of the network, which we know to be a likelihood of each category. We can use tensor TOPK to get the index of the greatest value. Type def category from output top n top I equal to output top k in bracket 1 category I equal to top I in bracket 0 item within bracket, return all categories, category I, then category I has to be typed. Finally, we'll print in bracket category from output in bracket output. Then click on run. You can see the greatest value is 5 for French. We'll also want to have a quick way to get a training example, a name and its language. Import random, def random choice within 1 in bracket. This will return a random number, return 1, random rand in it, 0 len 1, then 1, finally close the bracket. Then def random training example. This will fetch us a random training example. Now type category equal to random choice, all categories, line equal to random choice, category lines, category tensor equal to torch tensor, all categories, index category, then bracket close, type dtype equal to torch long, line tensor equal to line to tensor line, return category, type line category, tensor, then line tensor. For I in range in bracket 10, category line category tensor, line tensor, equal to random training example, print category equal to category line equal to line, you may take time to type. So after typing line, close bracket and let's run. So everything has run correctly. You can see the output that this little function made is so much easier to get a training example randomly. Now all it takes to train this network is shown in a bunch of examples. So make guesses and tell if it is wrong. For the loss function nn, n loss is appropriate since the last layer of RNN is nn log softmax. Hence type criterion equal to nn n ll loss then run. If you get error, then one L was short. Now we will find it correct. So each loop of training will create input and target tensors, create a zeroed initial hidden state, read each letter in and keep hidden state for next letter, compare final output to target, back propagate, return the output and loss. Now type learning rate equal to 0.005. If you set this too high, it might explode. If it is set too low, it might not learn. Def train category tensor, line tensor, hidden equal to RNN init hidden, initializing our hidden layer, RNN 0 grad, making all gradient to 0 initially to remove garbage values. For I in range, line tensor size, output hidden, RNN, line tensor I, hidden, this is getting the output scores for our hidden and output layers. Then type loss equal to criterion in bracket output category tensor, then loss backward. This is finally setting up the back propagation of a loss. Now add parameters gradient to their values multiplied by learning rate. For P in RNN parameters, P data add learning rate, P grade data. This will update our weights. Now we will finally return our output. So type return output loss item. So run. Now we have to run that with a bunch of examples. Since the train function returns both the output and loss, we can print it guesses and also keep track of loss for plotting. Since there are thousands of examples, we print only every examples and take an average of the loss. Now import time, import math, n iters equal to 1 lakh, print every equal to 5000, plot every equal to 1000, keep track of losses for plotting, current loss equal to 0 all losses in bracket. Let's also write a function to track time. Def time since in bracket since now time in bracket is equal to now since m equal to math floors in bracket s by 60 is equal to m multiplied by 60. Then return dm ts in bracket ms start equal to time. This will start our timer. For iter in range 1 n iters plus 1 category line, category tensor, line tensor, random training example, calling random training example from before. Next, type output loss equal to train category tensor, line tensor. This is calling the train function. Current loss equal to loss. This is to keep updating our loss. Print iter number, loss name and guess. If iter print every equal to 0, guess I, category from output in bracket output, correct if guess, category else wrong with a cross sign. Here you have to type carefully, and it's a long set of commands. Next is the person category, then print open bracket next type for f iter that is iter n iters multiplied by 100 times since start loss line guess correct. Next, add current loss average to list of losses. Type iter plot every equal to 0, all losses, append current loss by plot every. Next, type current loss equal to 0. Now we'll finally run this cell to start our training process. You can see it prints a tick if correct output is given, but you will find an error. So let's correct the error. Here there is a dash that has to be removed and equal to has to be put it. Then again run. We have found again it is showing error. Now you can see it prints a tick. Yes, error has come. Correct spelling has to be corrected. Then run again. Yes, now it's correctly showing. You can see it prints a tick if correct output is given and cross if networks gives wrong output. So meanwhile, let's understand application of recurrent neural networks. Image captioning. Remember, in last few videos we trained a CNN to classify our CIFAR-10 dataset. RNN can be used to caption the images, that is giving a description of what is happening in this picture. Another popular example is sentiment analysis. It is the process of computationally identifying and categorizing opinions expressed in a piece of text, especially in order to determine whether the writer's attitude towards a particular topic, product, etc. is positive, negative or neutral, or basically it is the study of emotions. You will be learning more about sentiment analysis in the next module. Another important and popular use is speech recognition. Speech recognition is using natural language processing, that is NLP algorithms like RNN, to identify words and phrases in spoken language and convert them to a machine readable format. Let's come to LSTM. It is long short term memory units or blocks which are used for building unit for layers for a recurrent neural network RNN. A RNN composed of LSTM units is often called an LSTM network. A common LSTM unit is composed of a cell, an input gate, an output gate and a forget gate. The cell is responsible for remembering values over arbitrary time intervals, hence the word memory in LSTM is used. They are widely used in chatbots, speech recognition, etc. As you can see in the architecture, left block is simple recurrent network which we are implementing. On the right hand side is an LSTM block diagram given. As discussed, the LSTM block has a memory unit which stores some information from previous iteration and passes on this information to the next iteration. Let's understand LSTM pros and cons. A RNN equipped with LSTM units is able to solve the problem of vanishing gradient in a network. This is an advantage. Again, due to a memory unit present in LSTM block, it is able to remember previously learned weights and adjust them in accordance with new weights. These are the marked advantages. However, disadvantages are the LSTM block is requiring a lot of computation power. A high RAM and GPU is required for training. Secondly, LSTM RNNs are slow to train. So now we will be plotting the historical loss from all losses, showing the network learning. Now type import matplotlib pyplot as PLT, import matplotlib ticker as ticker, next PLT figure, PLT plot in bracket all losses, PLT show. Then click on run. Then show and click run. Plot dot show. Yes, we get the result. You can see our loss had been steadily going down. To see how well the network performs on different categories, we will create a confusion matrix indicating for every actual language in rows which language the network guesses in columns. To calculate the confusion matrix, a bunch of samples are run through the network with evaluate, which is same as train minus the backprop. Keep track of correct guesses in a confusion matrix. Now type confusion equal to torch zeros n categories n confusion equal to 10,000. Def evaluate line tensor. This will return an output when it encounters a line. Type hidden RNN int hidden for I in range in bracket line tensor size 0 output hidden equal to RNN line tensor I hidden finally return output. Go through a bunch of examples and record which are correctly guessed. For I in range bracket in confusion category line category tensor line tensor random training example output equal to evaluate line tensor guess I equal to category from output in bracket output category I all categories index in bracket category confusion category I guess I plus equal to 1 normalize by dividing every row by its sum. For I in range in categories confusion I equal to confusion I divided by confusion I sum next set up plot type fig equal to PLT figure X equal to fig add subplot 111 next CX equal to X mat show confusion numpy next fig color bar cax setup accesses accept x tick levels plus all categories rotation equal to 90. Similarly for y tick levels copy paste and change x with y and remove rotation 90. that is till all categories. Then force level at every tick, type x-axis, set measure locator, ticker multiple locator 1, x y axis. So copy, paste, change x by y. Next, type Sphinx gallery thumbnail number is equal to 2, and then type plt show. Go to run, and will find a graph in as shown. Let us now understand the graph. You enlarge, you can now see, pick up the bright spots of the main axis that show which languages it guesses incorrectly. Example, Chinese for Korean, and for Spanish for Italian. It seems to do very well for Greek, but very poorly for English, perhaps because of overlap with other languages. Next, let's type def predict input line n prediction equal to 3, print n then percent input line with torch no grad in bracket and output equal to evaluate in bracket line to tensor in bracket input line. Get top n categories, type top v top I equal to output top k, n predictions 1 true, predictions in bracket for I in range in bracket n predictions value equal to top v in bracket 0 I item category index top I, 0 I, item, then print type 2F, then in bracket value, all categories, category index, next predictions, append value, all categories, category index. Let's try out our functions with a few test cases. So type predict dove sky predict Jackson predict Satoshi predict Udhab predict Shubham predict Dipanjan predict Ayan. Then press run. We'll find Dovsky, Russian, Jackson, Scottish, then Satoshi, Italian, Udhab, Russian, Shubham, Arabic, Dipanjan, Polish, Ayan, Arabic. As we have explained at the beginning of this class, the numbers beside this language are probabilistic score. Higher the score, the more certain is our classifier. This is all for today's session. We learn about RNNs, how to implement RNNs using PyTorch, and we trained a network to predict the language based on the surname. Hope you have understood well. If you have any query, don't hesitate to watch this video again. If you have any queries, you can send them to the following email address. Thank you.